Hello, welcome to section 1.5, which is on functions and logarithms. In this section, we're going to be talking about inverse functions, exponential functions a little bit, and logarithms, which are the inverses of exponential functions. So to start off, we have some vocab words. An inverse of a function maps the elements of the range onto the elements of the domain, which is the same thing as saying that the inverse of a function reverses the domain and range of your original function. Okay, a function f of x is 1 to 1 on a domain D if f of a is not equal to f of b whenever a is not equal to b. Well, that sounds like a really complicated definition, but really they're just saying whenever you have two different x values, right, then the x values are not equal to one another, then your y values are not equal to one another. So if I have two different x values, I can't go to the same y. So say, for example, I have absolute value of x, right? Then if I have absolute value of 3, then it's 3. And I have absolute value of negative 3, right? Those x values are different. So in order for absolute value of x to be 1 to 1, the y values have to be different. Well, they're not. They are the exact same thing. So therefore, this is not 1 to 1. Okay? Any function that is 1 to 1, when you have different x values, you will always have different y values. And you can test whether or not something is 1 to 1 by doing the horizontal line test. So let me grab my horizontal line. If I can draw a line anywhere and it only passes through the function once, then it is a 1 to 1 function. Right, we have the vertical line test to test whether or not something is a function, and now we have the horizontal line test to say whether or not something is 1 to 1. Okay, and this fails the horizontal line test, so therefore absolute value of x is still not 1 to 1. Why are those important in this section? Because a function that is 1 to 1 has an inverse function. Okay. Sure, if you have any sort of relationship, then you can reflect that over the line y equals x and get a new relationship. But to ensure that the new one is in fact a function, the original one has to start off as 1 to 1, which makes sense because if your original function passes the horizontal line test, when you reflect it over the line y equals x, that horizontal line becomes a vertical line, and therefore it's going to pass the vertical line test, and therefore it'll be a function. Next, do the following functions have inverses that are functions? Why or why not? Okay, the first one, well, this is going to look like a parabola. Who cares where the vertex is? This is a parabola, and therefore it is definitely going to fail the horizontal line test. So no, this does not have an inverse function. The next one, G. This is an exponential decay function. Usually if it was just 2 to the x, then it would be exponential growth. But because I have a negative x, I can know that it's exponential decay. Also, you can think about it the fact that we have negated the x value. It has reflected the function over the y-axis. So again, it is an exponential decay function. And then 3, of course, doesn't change anything because shifting left or right does not change whether or not a function is 1 to 1. So I can draw as many horizontal lines as I want to, and yes, it does pass the horizontal line test, therefore it is 1 to 1, therefore it does have an inverse function. Next, finding the inverse algebraically. We've done this before. All you need to do is switch the x and y in your original equation, solve the new equation for y in order to write y as a function of x. Okay, most of the time they're going to give you your original function in function notation, and therefore you should give your inverse in function notation. That is, write it as f inverse of x. So we have many steps to this example. So let f of x equal x cubed minus 1. First, we need to graph the function. So let me make this red. So if I plug in 0, right, normally I'd get 0 cubed if it was just x cubed. And then I'm going to shift it down 1, so therefore it is at 0, negative 1. If I plug in a 1, I get 1 cubed minus 1 is 0. If I plug in a 2, I get 2 cubed minus 1, which is 7. I think that's right. If I plug in negative 1, I get negative 1 cubed is negative 1, minus 1 is negative 2. Plug in negative 2, I get negative 8, minus 1 is negative 9. And it's a little bit easier to graph because all of these grid lines go from -10 to +10 on the x and on the y axes, just like your Zoom standard. All right, let me do the best I can. Oh yeah, that is not the best I can. And we want to connect our dots so that it looks like a cubic function. Not bad. Not bad. Would have been a little bit better on the board. Not bad at all. So, the next step says draw the line y equals x. Okay, I can do that with my fancy little computer here. Okay, and since this is a point 10, 10, then I can just go from 10, 10 to -10, -10, and that is my line y equals x. And I'll label it y equals x. Just let Mr. Wilson will be happy. I'll even label my original one as f of x to show the difference between my original function and my inverse function. Okay, next step says reflect the graph of f of x over the line y equals x. So we have these nice 5 little points here, and if we're reflecting over the line y equals x, then that means that we are switching the coordinates of our x and y coordinates at each of these points. So this point right here was at 2, 7, so therefore I want to go to 7, 2. 7, 2. This point was at 1, 0, so I'm going to go 0, 1. My next point was at 0, -1, so I'm going to go -1, 0. This point is -1, -2, so I have -2, -1. And my last one was -2, -9, so I get -9, -2. Oops, that's down here. And see how well I can connect these dots. Oh, I missed one. Not bad. And we'll label that f inverse of x. Make that a giant dot so it works perfectly. There we go. So, as you can see, right, they are crossing exactly at y equals x, because if I took this point and I reflected it over the line y equals x, it would still be exactly right there. So it's just a mirror image over y equals x. Find the inverse of the function algebraically. So I want to make sure that this is correct here. Obviously I can see that it already looks like a cube root function, and that would make sense because if I was to undo cubing it, then I would take the cube root. So I need to do just like I did, did I do that before? Well, maybe I didn't. The second time I recorded this, so I feel like I've already done it. Okay, so I want to, instead of f of x, I write y. So I have y equals x cubed minus 1. And I want to switch my x and y values. So I get x equals y cubed minus 1. And then I'm going to solve for y. So I'm going to add 1 to both sides. I get x plus 1 equals y cubed. And in order to solve for y, I'll take the cube root of both sides. So I'll go ahead and do that in this same step. So I get the cube root of x plus 1 equals y. And let's just write it as f inverse of x. I'll just stick it up here. F inverse of x equals the cube root of x plus 1. Very good. And by the way, right, I do not have to have a plus or minus because it is an odd root. If it was an even root, then I would have to, but then you have to make sure, was it 1 to 1, is your new one a function, and you have to pay attention to your domain and range. Okay. All right, next up, we're on E. Use your graphing calculator to verify your answer in part D. Well, I don't even need to use my graphing calculator because I know exactly what this function looks like. It's the cube root of x function, and it's shifted left 1. So my regular old cube root function would have been over 1 from all of those points. Here, I'll make it a rainbow color. Oh. Hopefully this will start working soon. I have not been having good luck today with this. Cancel. That's interesting. So anyways, I've already verified the fact that my new function does actually match the algebraic function that I found. What is going on? They're my babies when they were much, much younger. Okay, we're still recording. Yes, we are. That's weird that this Smart Notebook stopped working, but yet the recording did not. Sure, let's recover my lost files. Okay. Next step. Didn't miss out on too much. Very good. Okay, so verifying proving inverses. There's a couple things that you always have to do with inverses. You have to either find the inverse or verify that something is the inverse. In our next example, we get to do both of those things. So in order to verify that something is in fact the inverse, we need to check that f of f inverse of x and f inverse of f of x are both equal to x. Let's save this before I lose it. 1.5. Okay, so if my original function is x plus 3 over x minus 2, I want to find the inverse function. So I do just like what I did before. I have y equals x plus 3. Oh, yeah, I'll start off this way. And then switch my x and y. So y equals x plus 3 over x minus 2 instead of writing f of x. And then I switch my x and y, so I get x equals y plus 3 over y minus 2. And now I need to solve for y. So the problem is I have two different y's. I have a y here and I have a y here. And I just want to have one y so that I have y equals, then I have everything else on the other side. Okay, so in order to do that, first I'm going to cross multiply, or in other words, multiply both sides by y minus 2. And I will distribute that. So x times y minus 2 is xy minus 2x equals y plus 3. Okay, so still I have my y here and I have a y here. So anything with a y I'm going to put on the left-hand side. Everything else I'll put on the right-hand side. So xy minus y equals 3 plus 2x. And that helps me because now I can factor the y out of both of these terms on the left-hand side. So I get y times x minus 1 equals 3 plus 2x. And finally I get y equals 3 plus 2x divided by x minus 1. Okay, so since y was just being multiplied by x minus 1, I would just divide both sides by that. So that is my f inverse of x. Hopefully, I did not make a mistake. But if I did, we will see in a minute. So next we need to verify that that is in fact the inverse function. So I will start with f of f inverse of x, and hopefully I will just come out with x. And it is not enough to just do it one direction because oftentimes it'll be your domain will mess up and it'll work one direction and not the other direction. So you do have to check both, unfortunately. So now I want to take all of f inverse of x and plug it in everywhere I see x in my f function. So I'm going to take this whole thing and plug it in everywhere I see x in here. So that's here and here. So I get 3 plus 2x over x minus 1 plus 3 divided by 3 plus 2x over x minus 1 minus 2. Okay, in order to simplify this, I need to get a common denominator. So looking at the numerator of this whole thing, the denominator up here is x minus 1. So I want to get this one with the same denominator. So I'm going to multiply my 3 by x minus 1 over x minus 1. Same thing in the denominator, right? Still my common denominator in the denominator is x minus 1. So I multiply 2, or the negative 2, by x minus 1 over x minus 1. Okay, then I can distribute my 3. I get 3x minus 3, still over x minus 1. And since they have a common denominator, I can add them together. So I get 3 plus 2x plus 3x minus 3. And I can already see that this is working out very nicely because I have 3 minus 3, which will give me 0. And then 5x, hopefully I'll have a 5 on the bottom and those will cancel out. So my common denominator of x minus 1, and then my big line, and then the denominator I have 3 plus 2x minus 2x plus 2 over x minus 1. And whenever you are dividing fractions, then that's the same thing as multiplying by the reciprocal. So if I multiplied by x minus 1 over 3 plus 2x minus 2x plus 2, then my x minus 1s would cancel. So I can just cancel those ones now, so I don't have to keep writing it. And keep simplifying. So I get 3 minus 3 is 0, 2x plus 3x is 5x. In the denominator, I have 2x minus 2x, which is 0, and then 3 plus 2, which is 5. Cancel, cancel, equals x. Check. Wonderful. Very good thing. Okay. So now I just need to do the exact same thing, only the other way around. Let's do blue for that one. So I get f inverse of f of x this time. So now I'm taking all of f of x and I'm plugging that in for x in my f inverse function. So here's my f of x. So here's my f of x. I'm plugging this whole thing in everywhere I see x down here. So I have 3 plus 2, make giant numbers because I know I have to have a fraction here, 2 times x plus 3 over x minus 2 divided by x plus 3 over x minus 2 minus 1. 3 plus 2x. Good. Okay. And again, I want to make a common denominator, so I'm going to multiply the 1 by x minus 2 over x minus 2 and the 3 by x minus 2 over x minus 2. And since I can see that without writing it, I am not going to write it. So I get, right, I multiply by x minus 2. So I have 3x minus 6. Again, I have a common denominator, so I can just write it as one fraction. 2x plus 6. And the common denominator is x minus 2. This is all divided by x plus 3. And then I multiply by negative 1 by x minus 2, so I have minus x plus 2. All over x minus 2. Okay, and just like before, my two denominators are the same, so therefore they cancel. And I just want to simplify the numerator and the denominator. Negative 6 plus 6, 0. 5x divided by x minus x is 0. 3 plus 2 is 5 equals x. Yay, we did it correctly. So both of these are x, and you have to do both. Okay? If you didn't have to, I wouldn't make you do them both. Okay, let's save this. Next step, we're almost finished. One more page of notes, and then you just have your homework. Logarithmic functions. A logarithmic function is the inverse of an exponential function. So the definition says y equals log base a of x is the same thing as a to the y equals x. So a to the y equals x. These are the exact same thing. And next we have all the properties of logarithms. First one is our product rule. So log of a product then becomes addition. Log of a quotient, right? This is our quotient rule. Log of a divided by b is log of a minus log of b. Next we have our power rules that says that we can bring the power out in front. And then for these first three, I just did it as regular old log. Of course, they could all be the same. They could all be some weird base, as long as they're the same base, right? All of these could be, ooh, that's a highlighter. These could all be log base 7, 7, 7, and it would still all make sense. Okay, I just did the general version, so we didn't have too many letters in here. But I did stick more letters in here for bases. These next two are based off of the fact that logarithmic and exponential functions are inverses. So if I have a to the log base a of b, well then the log and the factor that's in the exponent undo one another, and we're just left with b. And same thing over here, your log and the exponent undo one another, and it is just b. Next one is your change of base formula. So log base a of b is ln of big number, whatever you're taking the log of, divided by ln of your base. Okay, so that's usually the way that we write the change of base formula, just because we like to use ln instead of any other base. But you could do log base 7 of b divided by log base 7 of a. You could do regular old common log, which is base 10. So log of b divided by log of a. You could do whatever base you wanted as long as they are the same base. And this is what I was just talking about with common log. Log base 10 of a is the same thing as just log of a without any subscript. And then the last one is log base e of a is ln of a. So that's called our natural log, and this is our common log. Okay, one more example. Evaluate the following without a calculator. I like these. So first thing we're going to do is we're going to set it equal to x, and we're going to solve for x because we want to know what this evaluates to be. So instead of writing it as a logarithm, I'm going to use the exponential form. So that's 2 to the x equals 1/8. Just a little loop-de-doo. 2 to the x equals 1/8. 2 to the x equals 1/8. And the goal here is that both of our bases should be the same, right? And since I know that 1/8, right, well that 8 can be written as 2 to the third, right? Then because it's in the denominator, then that's the same thing as 2 to the negative 3. So therefore, now that my bases are both 2 and 2, then it must mean that my, and here we go, that must mean that my exponents are the same. So therefore x equals negative 3, and that is my answer. X equals negative 3. So log base 2 of 1/8 is negative 3. Okay, how about this one? This one's a little bit trickier, but I'm going to start off in the exact same way. Set it equal to x. I have 27 to the x equals 9. And I can already see that these are both going to be products, are both going to be multiples of 3. So therefore, I can write them as exponents using 3. So this is 3 to the third gives me 27, and it's raised to the x. And 9 is the same thing as 3 squared. Well, how does that help me? Because 3 to the 3rd, and then raised to the x is 3 to the 3x. And that is equal to 3 squared. And again, since my bases are the same, then that tells me that my exponents must be the same. So all I need to do, save, undo, messing up my color coding. All I need to do is set my two exponents equal to one another. So I get 3x equals 2. So that tells me that x equals 2/3. So log base 27 of 9 is 2/3. Two more of these and I promise we are finished. Next, this one looks a little bit more complicated, but it's really not. So I still just have the same thing. I'm going to write it in exponential form instead of logarithmic form. 2 to the 5th equals x minus 1. Right, 2 to the 5th equals x minus 1. And I just want to solve for x, so I'm going to add 1 to both sides. Well, first of all, 2 to the 5th is 32, plus 1 is 33. That was easy. And last one. Oops. Okay, first of all, I'm going to divide both sides by 3. So I get 5 to the x minus 1. Yeah, that's not a multiple of 3, so therefore my answer is just 86 divided by 3. Okay. Alright, well now I need to solve for x when it's in the exponent. And the way that I solve for an exponent is by taking the log, or ln, or log base anything of both sides. So I'm going to take ln just because I like ln. So if I take ln of both sides, ln of this, ln of this, then I can bring my x minus 1 out in front, so I get x minus 1 times ln of 5 equals ln of 86 divided by 3. Well, I am going to do my quotient rule because I know I'm going to have a fraction later on, so I might as well not have a fraction within a fraction. So ln of 86 minus ln of 3. Okay, now I need to solve for x, so I'm going to distribute my ln of 5, so I get x ln of 5 minus ln of 5. I love logarithms. I think they're so much fun. I know, I'm no teacher though. Equals ln of 86 minus ln of 3. Okay. So now I can add my ln of 5 to both sides and then divide that answer by ln of 5. So I get x equals ln of 86 minus ln of 3 plus ln of 5. All divided by ln of 5. And of course I can't cancel these because that's addition and not multiplication. If it was multiplication, then I could absolutely cancel those. Up here, can I simplify that at all? That would be ln of 86 divided by 3 and multiplied by 5. Well, no, I can't cancel that at all, right? Because I can't cancel 86 times 5 divided by 3. I could write this all together, but I'm really not going to because I can't simplify anything at all, right? You could do 86 times 5 divided by 3, and whatever that number is, the numerator would be ln of that number. Okay. So, last page, on to the homework. It's exciting to have homework because then we're done with the notes. So your homework is just the examples from 1.5. There's nothing from the quick review, and these are very quick examples, especially 1 through 9 odd. You're just looking at graphs and telling whether or not something is one-to-one. Well, either the graphs or the equations. And the other ones are just right next to the examples that I just did in the notes, so you should be absolutely fine. I will see you tomorrow. If you have any questions, I will answer them then.